The other two cycle covers are the third cycle cover is we can crisscross using the edge which is horizontal. Okay, so that crisscrossing cycle cover. Go right, then down, then up and left down. And in this only exceptional weight is -1 due to the horizontal one. And in the final one we can use a self loop, the one which is at the bottom. So the bottom self loop is like this, and then a cycle above. Okay, so the weights are respectively 6, -2, -1, -1. Yeah, I missed one thing. This is actually 3. Yeah, so now weights are 6, -2, -3 and -1, which sums up to 0. So implies that weight sum of their weights is 6 -2 -3 -1 equal to 0. That is what we wanted to show, that cycle covers of XOR are actually not contributing anything. And what does that mean? So this means that necessarily in the big picture cycle cover, U has to be used. One of these UU prime, VV prime has to be used. If all of them are not used, then that cycle cover doesn't count. So let's remember that. So cycle cover of A prime involving XOR ij will necessarily use exactly one of the paths. UU prime or VV prime. Both cannot be used because UU prime path would already have covered these two extreme vertices. So either UU prime or VV prime will be used, and exactly one has to be used because otherwise the cycle cover doesn't count, weight is 0. So that is a good thing, which means that in the big picture cycle cover, this XOR gadget is forcing something on the variable gadget or clause gadget. This is forcing some cycle cover information on one of those. So consider such a cycle cover. Cycle cover C of A prime. So for all Cj, there exists an external edge say xi edge. Right, the clause Cj gadget has 3 external edges. So let's pick, say we are picking or the cycle cover is picking in fact not picking, dropping this xi, right? In the clause gadget we said that one will be dropped. So let's say xi was dropped, so not appearing in C. And now since this doesn't appear, so what happens is it tells you that which one of UU prime, VV prime. So in particular, VV prime is not being used. So then UU prime has to be used, and that means Xi is set to true. So this means that XOR ensures that jth external edge in Vi appears in C. And once the external edge is being used in the variable gadget, all the external edges will be forced to be used. So the same truth will reflect in all the clauses. So this implies that Xi equal to true is captured, is encoded consistently. In all clauses. Okay, this information is now consistent. So this is consistent to setting Xi true in all the clauses. Right? It's the assignment is what we have now encoded in the graph. So what we have achieved is that this cycle cover corresponds to a satisfying assignment of phi. Okay, so we have shown how cycle cover gives you a satisfying assignment. Cycle cover of A prime gives you a satisfying assignment of phi. And the converse also follows. Holds by the gadget definition. Okay, so we have set up a one-to-one correspondence between the cycle covers of A prime and satisfying assignments of phi. But still we are not done, because we have not computed the permanent yet of A prime, right? What we have achieved is a very big step, that we have set up a one-to-one correspondence between phi and cycle covers, but I mean assignments of phi and cycle covers, but we still have to check what is permanent, what is the value of permanent. So let us do that. So contribution of so we said that yeah, suppose UU prime is there in the cycle cover in the XOR gadget. So now let us see how much the XOR gadget contributes. So contribution of XOR, removing either UU prime or VV prime. Let's remove VV prime. To the weight is -2. And this is again a simple calculation looking at the definition of XOR gadget. So let's say let's see the paths from UU prime. They contribute so yeah, these 4 vertices, and UU prime is here. So you come like this, go up, down, and self loop. That's one. or what you can do is come like this, top, bottom, okay, this is also a path from UU prime where all the weights are 2 except all the weights are 1 except this being 2, or you can go down yeah, so that's 3 and there are 3 more. Okay, let's quickly finish them. And finally, this, and let me correct the weights. Weights are all 1 except these which I'm writing. Right, so you can actually check that from U to U prime. If you are using this path, then that's how the contribution to the cycle cover is done, right? Because you are forced to use this left edge, outgoing edge from U and incoming edge to U prime. This is U here, this is U prime. So there are these possibilities that come up. And what are the contributions from this part to the weight? So this implies that the weight contribution is 1 plus 2 minus 2 minus 1 minus 1 minus 1. So that is minus 2 as claimed. Note that the cycle cover contribution, when we removed UU prime, VV prime, then it was 0. But now we are saying, so that forced something to be used. So let's say UU prime is used. Once you use UU prime, then this will contribute to the bigger cycle cover of A prime, and that contribution is minus 2. Okay, so if this is 0, if you are working in a field of characteristic 2, then this will be 0, and this will then it will be a mistake in the reduction, because this again will be not contributing a cycle cover. So we don't want that. So this is why characteristic of the field should be non-zero. So the characteristic of the field should not be 2. That's why we don't want characteristic to be 2, otherwise this contribution becomes 0. And then permanent cannot be hard, because permanent actually is equal to determinant. So permanent and determinant are equal, mod 2. Right, so we don't want to work mod 2. That's a small assumption that you need, that the field has to be 0 characteristic or odd characteristic. And what this calculation shows you is that for a satisfying assignment, S of phi the sum over cycle covers C of A prime corresponding to this satisfying assignment. Note that although I said that it's 1-to-1, satisfying assignment corresponds to cycle cover, but the problem is that there are these multiple paths or cycle covers which the gadgets are introducing. We can count them, but still it is like one satisfying assignment S is giving several simply related cycle covers. If you sum up the weights, their weights, that comes out to be bigger than 1. Okay, this is why we are doing this calculation. So if we sum all these, then I get -2 to the 3m. Right, -2 for single XOR, and then there are 3m XORs. So this is the number of XORs, and this is the contribution from one XOR. And remember that this will be multiplicative, right? Because these XORs are different, so it's not actually additive. It's not -2 added 3m times. It's actually -2 multiplied by 3m times, because you can choose independently amongst XORs what cycle cover to take. So that's what you get, which now gives you complete information about permanent of A prime. So permanent of A prime is sum over cycle cover C of A prime summing over these weights, which is just the above thing multiplied by number of satisfying assignments. So it's -2 to the 3m times number of satisfying assignments, because each satisfying assignment gives you the same contribution. So we have just multiplied. So are we done yet? Just one thing remains. We claimed in the theorem statement that it's permanent with 0, 1 entries. Now we have actually used entries like -1 and 2 and 3. So we have to make it binary. So let's do that. Finally, we want A prime to be 0, 1 matrix. So for that, the idea is use modular arithmetic. And binary representation. So modular arithmetic is needed because to handle with -1, there is a sign, so just or -10, Since there is a sign, I can't just use binary representation. I have to also somehow encode the negative sign. So one good solution is that you actually do modular arithmetic. So -10 has a positive representation. Then use its binary representation. Write it down in binary. Okay, so let's finish this implementation. It's not difficult. What we did till now, that was the hard part. This is actually simple. So point is that if you look at the absolute value of permanent A prime, that is less than 2 raised to 3m was a factor, and the other was number of satisfying assignments, that 2 raised to n. So overall it is smaller than this, and let's call this let's define number, big enough number, this big N. It's just 3m plus n plus 1. And then we can work modulo this 2 power. So replace negative entry minus k in A prime by 2 raised to n minus k to get matrix A double prime, which now has only positive entries or non-negative entries, and you consider it's permanent modulo 2 raised to n. Right. So ultimately this will give you, I mean, since you already know 3m, so permanent A prime absolute value divided by 2 raised to 3m will give you the number of satisfying assignments, right? So let me write that down. So that value divided by 2 raised to 3m is the number of satisfying assignments. And this value you can find out. If it is positive, then permanent A prime prime mod 2 raised to n is that value. Or if it is negative, then you can take 2 raised to n. Then you can just take the negative of this. So the point is that it is easy to compute. Okay, the number of satisfying assignments you can still compute. And the only issue is how to now write it in binary representation. So A prime prime has non-negative but non-binary entries. So what you do is you replace weighted edge k by binary representation of k, introducing more vertices, more edges. So by a gadget of sequential and parallel weight 2 paths. So how to do that? So let's do this by an example instead of giving a general K proof. So example K equal to 5, replace this U to U prime 5 by the following. So basically use the fact that 5 is 2 square plus 1. That's the binary representation. So in graph terms, what you will get is from U, how do you compute 2 square? So you introduce many new vertices. Okay, so go from here that's parallel twos, parallel ones. So it gives you some 2. But you want 2 square, right? So let's repeat this. So now it is 1 plus 1 times 1 plus 1, so that's 2 square. So we have gotten 2 square path weight of the path contribution. 1 remains, so that I add another parallel path. Okay, so this is the picture of 5. Instead of single edge, that simple single edge, you replace it by a gadget which will not be very big. It will actually, since we are using binary representation, it's logarithmic size, log k. So the gadget has size big O of log square k. Log k is the number of bits when you write k, and yeah, just check that there will be a certain blow up, but it's only quadratic, it's not super quadratic. In this doubling, we are actually making copies, so that is log k times log k. So finally we get we get 0 1 matrix, this A prime prime. Is it A prime prime? No, from A prime prime we will get the matrix A. So this transformation, this gadget will convert it into A of dimension only polynomial in n plus n. Right. So to check whether it's really polynomial in m plus n, see this, we went mod 2 raised to n power. So the bit size was n, big N, which is around m plus small n. And we are taking log of, so when we look at log square k, that's actually something like m plus n square. So that fits the bill. And the graph size was, there were n vertices at all times, right? So now that n vertices, they have blown up, but not more than poly m plus n. So this exactly you can actually compute how much it is, but it suffices to say that it's poly, and the relationship is permanent of A mod 2 raised to n is equal to this. You can check. Okay, so mod 2 raised to n, it will come out to be this. So for positive, it's for m even, this is an exact equality. For m odd, you can use the negative remainder, and in both the cases you will, by division, you will get number of satisfying assignments. And you remember that division by 2 possible if and only if characteristic of the field is not 2. Okay, for any characteristic except for any odd characteristic, 0 characteristic, 1 by 2 is there in the field, so you can divide and get number of satisfying assignments. And this tells you that counting sharp SAT is solvable in efficient in this functional polynomial time class using permanent on 0, 1. And which means that sharp P can be solved using permanent, because sharp SAT is the hardest problem, right? So sharp P completely can be solved. That is what we had promised in the theorem statement. So permanent is sharp P hard.